Okay, good afternoon, good evening to everyone. We are very pleased to present Roberto Bernal from UAM Coajimalpa. He's going to present work on Kullback-Leibler divergence in machine learning. Please go ahead, Roberto.
Yeah, thank you very much. And I want to thank the organizers of these talks, and thank you very much for inviting me. I'm very happy to be here sharing part of my job. And as the presenter said, we are going to talk about the Kullback-Leibler divergence in machine learning and how it's related to the cross entropy. That is one of the main concepts in machine learning. And well, we will see how it is applied to the Boltzmann machines. First of all, we want to say that Kullback-Leibler divergence is a fundamental measure in information theory that quantifies the difference between two probability distributions. This concept has been widely adopted in machine learning due to its central role in training probabilistic models and optimizing objectives based on comparison between distributions. This talk will cover several concepts like what is the KL divergence, how is its interpretation as a measure of discrepancy, and its relation with cross entropy, because this is one of the main goals of this talk, and the application to Boltzmann machines. Okay, first of all, we want to say that talk about entropy. Shannon entropy measures the uncertainty or randomness of a probability distribution. For a discrete distribution P, entropy HP is we have the definition that appears in the screen. H of P is given by the summation of P of X times the log of P of X. And then high entropy implies high uncertainty, low entropy implies predictability. Then cross entropy, the cross entropy measures the difference between two distinct distribution, P and Q. For instance, we can have two distributions, and then we want to say, well, these are not the same, but we want to measure, quantify. Yeah. Oh, sure. I'm sorry. Then let me change my. I will use another. I will focus my camera, and then I will open this with another program. Maybe with this program is better to see the visualize. Okay. Okay. There is there. I hope that you can see now. And if something, okay. I don't know if you can see the slides. Okay, I will make some transitions. This is a transition, then you can see it. Okay, okay, okay. But it's in automatic, then I have to be careful not to. Okay, then I was, I'm sorry but for this, but I was talking about the Kullback-Leibler divergence. It is a fundamental measure in information theory, no, that quantifies differences between two probabilistic distributions. I was stating that, and at the same time, I was telling that well, this is a main concept and is widely used in machine learning due to its central role in training probabilistic models. This talk will cover several of the concepts of the KL divergence, its interpretation as a measure of discrepancy, its relation to with cross entropy, and application to the Boltzmann machines. No? Then, first of all, I want to talk about entropy, Shannon entropy. It measures the uncertainty of randomness of a probability distribution. For a discrete distribution, we have this definition that appears on the screen. Then we can see that Shannon entropy is well defined. H of P is equal to minus the summation over X of P of X log of P of X. High entropy implies high uncertainty. Low entropy implies predictability. Then what is cross entropy? Cross entropy measures the difference between two distributions P and Q. It's something similar to the KL divergence. I mean, and then the cross entropy measures the difference between two distributions. We are stating here the definition of HPQ is equal to minus P of X log of Q of X. This definition is using classification tasks to compare predicted probabilities Q with true labels P. No? That means that we have distribution and very well known distribution, and then we have a model that is giving us some data distributed as Q of X. And then KL divergence is another definition, measures how one probability distribution, P, diverges from a reference distribution. Then the definitions is given by the summation of over X of P of X, the logarithm of P of X over Q of X. This Kullback-Leibler divergence has some properties, the important properties, like it's non-negative with equality only if P is equal to Q. Only if these two distributions are equal, then in that case, we will have that the equality. And non-symmetric, that means that if I calculate the KL divergence of P P with respect to X as is will different of Q with respect to P, no? In other words, KL that measures the differences between two probability distributions. P is the true distribution and Q models is the model distribution. And then once we have this definition, we can investigate and we can see how this Kullback-Leibler divergence is related to the gross entropy that was given in the last slides. Then the relation of KL divergence and gross entropy, it can be established easily because if we use the KL divergence definition, we can, as appears in this, we can develop this term in two terms, that is the cross entropy and the entropy of P. Is the sum is the two terms. One corresponds to the cross entropy, and the other one is just the entropy of P. This entropy of P, as P is well known and is the data that we have, then this is a constant. This is the entropy that is not going to change during our processing, which we want to see if which are the differences between the two distributions. Then this last term, P of X, log P of X, is just the entropy of P and is a constant. And then the other term is just the cross entropy, and then we have that Kullback-Leibler divergence is simply given by two terms. One term corresponds to cross entropy that was given before, and the other term is given by a constant. Then if we minimize one, we can easily relate to the minimum of the other. That means we can establish a relation between the Kullback-Leibler divergence and the cross entropy. And this relation is given by the Kullback-Leibler divergence, as appears in this equation, will be given by the cross entropy minus the entropy of P. Then this from this relation, we can see that if we can minimize to minimize the cross entropy is equivalent to minimize the Kullback-Leibler and vice versa. We can minimize the Kullback-Leibler divergence, and at the same time it's equivalent. It's equivalent to minimize the cross entropy. This is a very useful relation, especially in machine learning, because many, just when you are working with machine learning, sometimes just to work with the Kullback-Leibler divergence is not very easy, but to work with the cross entropy is easy. Then, but we are seeing that is to minimize one is just equivalent to minimize the other. Then if we are working, for instance, in any problem in machine learning, we just have to minimize the cross entropy. This is a very good point, especially when you are working with a long, huge amounts of data. Okay, relationships, well, we have established this relationship that the divergence, the KL divergence is related with the cross entropy. This, as I said, this is very useful, especially when we are working in machine learning, because when we have, suppose that we have this distribution that appears in orange, and this distribution is the true distribution. And then we will use a neural network that has, but suppose that we want to just use a neural network that is a mathematical function with enough expressive power to capture complex patterns that are in the data. Then we are just approximating this through, let's say, through distribution with another distribution, and then we want to approximate one with the other, using this kind of model that is a machine learning. That is a neural network. And in order to do that, we have the objective that we will have is to minimize this divergence, and then in that case we will have that the two distributions will coincide. As we see, the only thing that we can do, the only thing that we have to do is just to minimize the cross entropy. That's why in many books, when you see in many articles, in many works, when you can see that it's only enough just to minimize the cross entropy instead of having another technique just to minimize the Kullback-Leibler divergence directly. Then this is of great help, especially in this kind of models in which we are looking that the output of this neural network, we want to coincide with this distribution that is the true distribution. Let's say that is the true distribution. We want them to coincide. And then as we want them to coincide, we have to minimize the KL divergence. And well, as we see in the process, this model is approximating if and only if we minimize the cross entropy term. This is the procedure in which machine learning is based, in which you have to use the model. You are just training with the true data, and then this mathematical model will try to resemble this the true data. But the thing is that we have to do this kind of procedure using the cross entropy in order that the two distributions coincide. Okay, then in machine learning, minimizing cross entropy loss, that is, as it is called, this function, cross entropy loss, implicitly minimize the KL divergence, aligning the model distribution K with the data distribution P. That's very interesting how these models, machine learning models, are just trying to imitate and to give some distribution with this model, and that give another distribution that is not the original distribution, and then at the end it grasps the most important characteristics and patterns that are given in the true distribution, and then tries to reproduce this in the other distribution. And well, mathematically speaking, we are just seeing that this is equivalent to minimize the cross entropy in order that the two distributions coincide. Okay, once we have established that this can be done in this kind of machines, for instance, we can do there are different kinds of neural networks. For instance, this kind of neural network that I was talking about, this is a recurrent neural network, or could be also a neural network that has backpropagation, in which you are constantly just trying to correct the weights of the model in order that the cross entropy will have a minimum, will reach its minimum. And then, but there are all other kind of models like the Boltzmann machines that are very important in physics, especially because it resembles some of the physical models that we have, like the Ising model and other models with magnets. And this is why Boltzmann model is so important. And besides, is based in statistical mechanics. When it was given by Hinton, he was basing his work in statistical mechanics. Then, but what is a Boltzmann machine? A Boltzmann machine is a stochastic neural network that learn probability distribution over data. Is again, we are learning a probability distribution. We give some data, and then this model tries to learn this probability distribution, tries to grasp the main characteristics of this distribution and try to reproduce and imitates and to reproduce the original distribution. Okay, and then well, consists of units. These units are called neurons, and it has two kinds of units. One is the visible part, and the other is the hidden part. And then these parts are symmetric. I mean, they have connections, as we will see in the figure. For instance, we have a figure. For instance, this is the visible layer. This is the hidden layer. And then every neuron, every unit of the visible layer is connected with the other neurons in the hidden layer. If you see here, unfortunately, some arrows appear, but the thing is that this connection is for going from the visible layer to the hidden layer, but also in the second part of the iteration, you will go from the hidden layer to the visible layer. Then the arrow is not really correct because you can say that this is undirected graph. This is not directed. And then once for training this kind of, as we will see, for training this kind of Boltzmann machine, you go first from the visible layer in which you introduce your data, and then this is the input, and then the hidden layer. And the hidden layer returns your data once some modifications are given, and then again is trying to reproduce what's in the input layer. I mean, trying to reproduce, trying to give new data that corresponds to the same distribution. Well, and this kind of machines are energy-based models. The probability of configuration is given by this probability density. Well, it has implicit an energy function and a partition function that is completely based on statistical mechanics. The energy function is given by resembles to other models like spin models, etc. But this energy function is given by B and H are the visible parts and the hidden parts, and it has some weights, no? That in this, the visible units and the hidden units are named B and H respectively. And also we have a matrix that is connecting, that is, having all the weights and the weights that connects these two parts, the visible and the hidden. And then at the same time, we have some other parameters that has to do with, are called bias. And this bias affects directly the visible units. A, for instance, is the coefficients. Every visible unit has a coefficient, and every hidden unit has also a coefficient that is called bias. And then it can be given in also in matrix form, but here I didn't use the metric form. It's just simply, it's like as you can see, this is simply like a dot product between two vectors, no? and A and B and H. And here is a matrix product. That can be seen also as a matrix operation. Then, what was the objective in this kind of machines? The objective in this kind of machines is minimize the divergence between the data distribution and the model distribution. There are two data, the data distribution that you are given in the input units, and then the model will return you some data that is the P of the model. And then, well, the objective is to minimize the divergence between these two distributions. Yeah, then it has to be a procedure in order to have, let's say, good data as a response of the Boltzmann machine, because you will give some data that is the input data, and then the machine will return you some other data that is the model data. But in order that this model data is approximating, we want to approximate this model data to the distribution data, the true data, then we have to minimize again the divergence between these two distributions. And for this, again, we have to minimize the KL divergence if we want to have this new data that is because the magical thing of this Boltzmann machine is that it's giving new data but that corresponds to the distribution that you are that you are working with. That means that if you train your machine in a suppose and then you minimize the KL divergence, then what you will have in return of this machine, the machine will be giving you a new data for that corresponds to the distribution in which you are working with. Then well, there are several mathematical steps in which you can follow, but at the end you have a procedure in which the gradient descent is used in order to minimize the divergence, the KL divergence. And then you will have the expectation values of the data minus the expectation values of the model will be given by this matrix Wij. The variation of this matrix will be proportional to this difference between the expectation values of the data and the model. And then gradient-based optimization is used to update the weights, and the challenges is computing the partition function is computationally expensive. Then there are some tricks in order to avoid to use the partition function because it's practically really, so you cannot really have a way to have all the I mean the cases, and it's almost impossible to have the partition function unless you have a very simple problem. Then the thing is that the applications for the KL divergences and these machines is you can approximate the complex and posterior distribution in Bayesian models. Also, these machines are used for generative models because you can generate new data, training this kind of machines, training this kind of models. You can have new data. That is very important in many cases. And also is used in reinforcement learning and this kind of machines. No? And well, just almost finishing, I want to say that Boltzmann machines use KL divergence to learn representation of data and ensures that the model distribution matches with the data distribution. KL divergence is a fundamental tool in machine learning for comparing distribution. This is my conclusions. It is closely related to the cross entropy, making it essential for classification tasks like in the neural network. And Boltzmann machines leverage the KL divergence to learn complex data distributions. And well, in future work, we will try to do scalable training methods for Boltzmann machines and other energy-based models. Okay, that's all, and thank you very much for your attention. I want to thank you for your attention, and I don't know if you have any question, any observation. Thank you very much.
Thank you for your interesting presentation, Roberto.
Mm-hmm.
We appreciate your participation in the event.
Thank you very much.
I'd like to remind the attendants that any questions can be forwarded to the channels at Zoom and YouTube, if you wish.
Yes.
Thank you very much, Roberto, again.
Yeah, thank you. Thank you.
Okay, our next speaker is Saúl Salazar,
Yes, I am here.
presenting construction and analysis of information measures through Diophantine equations. Go ahead, Saúl.
Thank you. I share my presentation. Can you see my presentation?
Yes.
Yes, Roberto. Sorry,
Okay.
Saúl.
Well, thank you, Rodolfo. Hi, everyone, and welcome to my presentation. First of all, let me thank you for coming here today. And my talk is titled Construction and Analysis of Information Measures through Diophantine Equations. Now, my talk is divided in 3 sections. In the first section, I talk about the background of this work. Then I talk about some preliminary results. And finally, I try to introduce some conclusions and perspectives of this work. So first, let me start by saying a few words about the background of this work. I mean, the study and quantification of correlation effects, I think that are very important aspects of the many-body problem. Also, in general, these effects are due to the interaction or correlation between particles in a given system. So we can ask this question: why do we study correlations between interacting particles? In this case, we study quantum systems. So in our studies, we try to use quantum harmonic oscillators. So interaction between particles, I think that we study quantum systems is necessary to consider the position and momentum spaces. Also, in this sense, we can establish a relation with the particle indistinguishability, I mean, between the symmetry or antisymmetry of the wave function to prove some difference in this kind of systems. Other important aspect is to study the effect of potentials. In this sense, we can study the potential of one body, also the potential of 2 bodies, or maybe the potential of three bodies. I mentioned that we can study the symmetrization of the wave function. In our case, we study quantum systems related with 3 harmonic oscillators. And finally, we can study uncertainty principles. For example, we know the Heisenberg uncertainty principle that could be reformulated or recast in terms of the information entropies that are the uncertainty measures taken from information theory. So in this sense, we believe that this principal uncertainty is very important aspect in the information theory to study this kind of quantum systems. So now I continue with the model. In this sense, I introduce the quantum harmonic oscillator system. So we start with this Hamiltonian related with n-coupled oscillators in canonical coordinates. In this Hamiltonian, we can observe the central potential that is related with this parameter omega. And also in this term, we can observe this parameter related with the pair strength correlation between two particles. So in this sense, we can introduce a new Hamiltonian in the Jacobi coordinates. So this is important because we can solve the Schrödinger equations in the new Jacobi coordinates. When we use these Jacobi coordinates, we can introduce new constants. This alpha 1 is related with the one-body potential squared, and so on until alpha n that is related with the one-body potential and other parameters like the number of particles and also the pair strength potential. I also mentioned that in this Hamiltonian, for n couple oscillators appears this sinus, plus and minus, and the sign plus is related with attractive potential, while the minus sign is related with repulsive potential. So when we have the change of these coordinates, we can solve the Schrödinger equation, and the Schrödinger equation can be solved exactly in the Jacobi coordinates. Thus, the Hamiltonian is rewritten in the new coordinates, as you can see in this slide. With this change, we can obtain the gain functions in these new coordinates. So we can define in this new Hamiltonian new parameters related with the subscripts and the relation with the quantum numbers. So the new eigenfunction function that we can get, we can written as a product of different eigenfunctions related, for example, with the coordinates of the mass and the relative coordinates. So each of these eigenfunctions can be written in terms of a function, an Hermitian function, and also Hermite polynomials. Finally, we can get the density function that corresponds to the density for n oscillators. So in this sense, this constant is a normalization constant. Now, we can establish the goal of this work. So I think that in this sense, we can examine how physical constraints imposed upon the system affect the behavior of the information measures and their interpretations. I think that is very important. In the previous works, have studied analytical relationships of informational measures of pairs of variables, such as mutual information or higher orders, such as total correlation and interaction information in quantum systems, in the particular case of harmonic oscillators. So we can study this kind of measures as a function of the two-body potential that call it the parameter lambda, and also with the number of particles n. Now we can mention some definitions related with the information theory. So I think that the more important definition is related with the Shannon entropy. So the Shannon entropies are measures of the uncertainties that appears in the underlying distributions, and these distributions have been used to examine quantum systems. So the interpretation of the Shannon entropies in that, they are measures of the localization in the underlying distributions, where larger values correspond to more delocalized distributions, while smaller values are indicative of more localized ones. Well, in this sense, we can define the reduced densities. In this sense, we can define the rho related with one particle, gamma that is related with 2 particles, and theta that is related with 3 particles. With this definition of the reduced densities, we can establish the definition of the corresponding entropies. So the entropy of 1 variable, the entropy of 2 variables, and the corresponding entropy of 3 variables. This 3 variable distribution is called the parent distribution because I mentioned that I work with a system with 3 particles, is the main density. So maybe reduced by integrating over one of the variables to yield a 2 variable distribution. A further reduction by integration can be carried out to yield the 1 variable density. So we can continue with the definitions related with important concepts of the information theory. So I think that other important concept in the theory is the pairwise correlation between 2 variables that can be quantified in terms of the mutual information. In this sense, the interpretation of this variable, of this measure, is that it is a relative entropy between the 2 variable distribution and a reference, which is the product of 2 marginals. In this sense, pairwise mutual information is bounded below by 0, which corresponds to a separal distribution. In this definition, we can observe the integral form in this part, and in the other side, we can observe the definition related with the corresponding entropies. Also, we can define the mutual information in terms of the Venn diagram that appears below. So in this region that is called R2, we can observe the mutual information, while in this region called R1, we can observe a relative entropy, and in R3, we can observe the other relative entropy in terms of the relation between the entropies between a system of 2 particles. Now we can establish new definitions related with higher order correlation. The one can also consider these kind of measures among 3 variables. So the first definition is the total correlation that is defined as this. And this total correlation measures all the distinct types of correlations in the system. Also, we can observe the integral form, and we can write this total correlation in terms of the corresponding entropies. Also, we can define another higher order correlation that is called per particle correlation that appears here. And we can continue to observe that exists a definition in integral form and also in terms of the corresponding entropies. Finally, we have studied interaction information, and this interaction information, which takes into account the correlation or interaction among the 3 variables in the system, and it is given as this expression in the integral form, and also we can write this definition in terms of the corresponding entropies. In this sense, we can expand the sum of these 3 terms of the entropies in this other form. It's important to observe this definition because this definition is called synergy, and the synergy is the first term of the interaction information. So this is a new definition of a higher order correlation. This interaction information could be a positive value or negative value, and that depends on of the value of these terms. So the first term is the synergy, and the second term is called redundancy. This term is defined as 2 times the mutual information. In this diagram, we can summarize all definitions of the higher order correlations. I could say that this region called R7 is related with the interaction information, and this region measures the interaction between, or the interaction among the 3 variables of the system. And this is very important in our work. And also we can observe other kind of regions that are related with the relative entropies and the other definitions of the higher order correlations. So these Venn diagrams are very useful in this sense, to establish the relations in a diagrammatic scheme. Now, we can mention, I can say that in this work, we try to examine the expressions of the mutual information, the total correlation, and the interaction information. And we can infer that it is possible to construct them from the definition of certain coefficients associated with linear combinations of the Shannon entropies. But first, I think that it is necessary that I call about the Diophantine equation. In a general form, a Diophantine equation is an equation that has a polynomial form, and this polynomial equation could be monouns with integer coefficients, and also has integer solutions. So this kind of equations appears in the theory of numbers, and it's important to say that this is a kind of linear Diophantine equation that is related to a Besut identity that is very important in theory of numbers. So Diophantine equation is defined in terms of the sum of these entropies, the entropy of 1 particle, the entropy of 2 particles, and the entropy of 3 particles, and appears the integer coefficients n, m, and l, and this equation is equals to 0. We can consider that this is an homogeneous equation in mathematical terms, where the coefficients of the linear combination of the entropies can be defined in terms of 2 new integer coefficients. I mean, the n coefficient is equals to C1, the m coefficient equals to C1 plus 3C2, and the coefficient L equals minus C1 minus 2 times C2. These new coefficients, C1 and C2, are also integer numbers. By construction, if we study systems of 2 particles, I mean when n is equals 2, we fixed the coefficient m equals minus z minus 1. And finally, if we study systems of 3 particles or variables, the coefficient L equals minus 1. This idea appears in this paper in a seminal form. Now, we can consider that if have a system of 2 particles or variables, we can get or we can obtain the coefficients C1 and C2. So if C1 is equals 2 and C2 is equals minus 1, we get the mutual information. And these 2 numbers are solutions of the Diophantine equation, of the corresponding Diophantine equation. Now, if we pass to the system of three variables and assign the corresponding number C1 like as 3 and C2 as -1, we get the total correlation. Now C1 equals 1 and C2 equals 0. We get the synergy. C1 equals -1 and C2 1. We get the per particle correlation. And finally, if we assign C1 equals -3 and C2 equals 2, we get interaction information. So in this sense, we have a question related with the procedure with this solution of the Diophantine equation to obtain new correlation measures. In this sense, we use this kind of interaction correlation measures, but we don't know if it's possible to get or construct new measures related with higher order correlation, and also if this kind of measures has a significance or a meaning physical or relevance in the physical system. Also, we can think that this procedure we can useful to get new correlation measures related with the number of particles. I mean, we can get correlation measures related with 4, 5, 6, or some particles. This is the kind of questions that we have done when we observe the relation between the Diophantine equations and the informational measures of higher order. Now, I mentioned some preliminary results related with the interacting quantum harmonic oscillators, both in the ground state, because by this system, we get analytical solutions. In this sense, it's important to establish an analytical solution, because with this analytical solution, we get a good results related with the interpretation. So one of these principal goal of this interpretation related with the interacting quantum harmonic oscillator is that we want to examine the particle number dependencies when we have attractive or repulsive interparticle potentials that appears in the Hamiltonian. And also, we present and analyze the independent behavior of the measures and their dependencies on the interaction strength that has the two parameters of control. So you can see in this slide 4 plots related with the informational measures for 2 variables and 3 variables versus the parameter lambda. This parameter lambda is related with the per strength correlation. So in black, we can see the mutual information. In red, we can see the total correlation. In blue, we can see the synergy. In yellow, we can see the per particle correlation. And also we set other parameters like omega equals 1, and also the number of particles related with the mutual information for 2, and the other correlation measures with the number of particles 3. So this figure presents the behavior of the attractive potential related with this column at the left, and in the other column at right, we can observe the repulsive potential. Also, the magnitudes of both measures are different in each space. I mean, we can observe in the first row the position space and below the momentum space. So this type, the dominant interaction can be tuned, can be controlled with the coupling of strength potential. The difference here is that this change occurs at a larger coupling set strength, while in the attractive potential, this occurs at a smaller coupling strength. We can observe the increasing of the measures by larger values of lambda, and also it's the same behavior by the repulsive potential. Now, in this slide, I present the informational measure related with interaction information versus the same parameter lambda. And also, we set the omega parameter equals 1 and the number of particles 3, because this is a measure of higher order. In red, in the first row, we can observe the position space, while below, in blue, we can observe the momentum space. In this figure, we can observe that the magnitudes of both measures are different in each space. Also, this type of dominant interaction can be tuned with the coupled strength. And the difference here is that this change occurs in the same way. I mean that for these kind of the systems, for the position space and attractive potential, we can observe that this measure is negative, and also for the repulsive case and the momentum space is negative. This vertical dashed line corresponds to the bound of this potential, while for the attractive case rated with the potential at the momentum space, we can observe that this measure is positive, and also this occurs by the case of the repulsive potential and position space. Now I present the study related with the informational measures, but now versus the number of particles. In the same sense, the figures or plots in black corresponds to the mutual information. The plots in red corresponds to the total correlation. In blue, the synergy, and finally the per particle in yellow color. Also, we fixed omega equals 1 and the value of the per strength correlation equals 1. So in this case, we can observe that all informational measures have a corresponding behavior. I mean, in this case, by the position space with attractive potential, we can observe that this informational measure decreases when we increases the number of particles. This behavior is equal by the attractive potential in momentum space. But, for the case of the repulsive potential, we can observe that the informational measure increases when the number of particles also increases, in both cases related with the potential. And finally, we can show the corresponding plot related with the informational measure for higher order, in this case related with the interaction information. In this row, in red, we can observe the case of the position space, and in blue, we can observe the momentum space. In this column, the attractive potential, and in this other column, the repulsive potential. Also, we fix the parameters omega equals 1 and the parameter lambda equals 1. In these informational measures, we can observe that grow in magnitude as the value of the parameter lambda increases, and in the interactive and repulsive cases, in the respective bound that I show, like this vertical dashed line corresponds to the bound for the repulsive potential. And also, this interaction information presents changes of the sign with the type of the potential, as the other case related with the same informational measures versus the lambda parameter. Well, with these preliminary results, because this is not a finished work, we present some conclusions, and these conclusions are related with the plots that I present you. First, we observe consistency in Shannon's informational measures of higher order correlation by pairwise mutual information when we modulate or tune the parameters lambda related with the pair strength correlation and the number of particles. This is a consistency between these informational measures that was being observed in other papers or works. Also, the interaction information is observed that there is also consistency. In this sense, I try to separate this informational measure because it has a change of sign if we compare with the other interaction information of higher order. So these changes of sign depends on the potentials when vary the system. I mean, in the case of attractive or repulsive potential, and also that depends on the position space and momentum space. Finally, I mentioned two perspectives. One of these is that we want to get new correlation measures of higher order using this kind of procedure when we solve Diophantine equations. We believe that this procedure has a good reason to survey and has relation with other branches of mathematics. For example, we think that there are connections between chromatic polynomials in theory of graphs, and there are many ideas related with this survey. And finally, we want to explore these measures in other kinds of quantum systems. In this sense, I would be interested to explore these results in other systems. I mean, in excited systems of quantum harmonic oscillators, or maybe in atomic atoms. I don't know. Well, and finally, I don't know if you have any questions. I will be happy to answer them in the chat. So thank you for your attention.
Thanks for sharing your work, Saúl.
Okay, thank you.
We appreciate your participation. For that, in this of today's sessions, thank you for participating. Again, you all might forward your questions or comments to the channels of the event at the Zoom and YouTube channels. And well, this is all for today. We invite you to join again for tomorrow's sessions at 9 a.m. UTC and -6 time. See you tomorrow. Thank you.
Thank you. Bye.